Hi everyone, in this video we are finally going to discuss a nuclear half-life. So now I love nuclear half-lives because it is basically a mathematical problem for nerds. And so if you're a nerd like me, you're definitely going to like this. If not, just hang on and get through this video. So let's start off with a very simple definition to get started here. So what is half-life? Well, half-life, first of all, is usually represented by a lowercase t, and then it has the subscript of 1/2. So it's the amount of time it takes to decrease something by half, all right? So let's give a real definition, though. It is the time required to decrease the initial level of radioactivity by half. Okay, so if we start off with something that has a level of radioactivity of 100, let's just pick some random number, we want to know exactly how much time it's going to take to decrease that level of radioactivity of 100 down to 50, okay? Now that exact same time frame is going to exist when you take that sample from 50 to 25. Same amount of time when you take it from 25 to 12.5. So the time increment is never going to change. It's always going to be the exact same amount of time that it takes to decrease that sample by half. So now, two things I want to point out. The first one is that the half-life is 100% independent of temperature and pressure. So regardless, if you have a lot of high pressure or if you have something that's a very high temperature, it is not going to change that half-life. Now, the second thing I want to point out is that your half-life very varies, okay? It's very variable. It entirely depends on what your sample actually is. If you're looking at a sample of uranium-238, you have a huge half-life. If you're looking at something like polonium, something that's very tiny, you have a teeny tiny half-life. So let's actually look at a graph of this so we have some numbers, or a table, I should say. So, on the left side, we have all of our radioisotopes, and we're ranked from something that has a very large half-life, like uranium-238, which has a half-life of 4.5 times 10 to the 9th years. That's huge. That is a huge amount of time that it takes for one sample to decrease its concentration by half. Let's move down a little bit, closer to something like carbon-14. Carbon-14 still has a very long half-life of 5,715 years. So I will never ever experience the half-life of a carbon-14. But I will experience something like thorium-234 because its half-life is only 24 days. I've definitely lived for 24 days. And if you come down here all the way to the bottom, like I mentioned earlier, you have polonium-214, which is a half-life of 0.00016 seconds. That's teeny tiny. It basically goes from a concentration of 100% down to 0 like that. Okay, so fast. So using this table and this information I've just provided, I want you to answer a question. So here is my question. Which isotope, and I'm going to give 4 of them to you, I'm going to provide 4 isotopes, will be considered radioactive? So remember what that term means, radioactive, for the longest period of time. Okay, so which one of the following 4 would be considered radioactive for the longest period of time? All right, C14 is one option. Cesium-137 is another option. Uranium-238 is one option. And then radon-222 is another option. Which one will be radioactive for the longest period of time? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. This is a very new concept, so don't get frustrated if it just doesn't make sense yet. So the way I would have approached this is I would have gone through and figured out the half-life for each one of these 4 isotopes. So the first one was carbon-14. So if you look at our table, we have carbon-14, which I've starred over here, and we see that it has a half-life of about 5,715 years. So we're talking about years for this one. The next one was cesium-137 here. That has a half-life of 30 years. So again, we're still talking about years for our unit of time. Uranium-238 has the longest half-life, and we're actually talking about billions of years for this one. And then the last one we discussed was radon-222, and that has a half-life in days, so days only. So what you do here is you say, all right, half-life of days, definitely not the longest. Half-life of years, not the longest. Half-life of billions of years, that is 100% definitely going to be the longest, and uranium-238 was definitely 100% the correct answer here. All right, so now we've discussed half-life, we've discussed numbers of half-life, but sometimes this just isn't enough to solidify this concept, and I actually feel that working through an example helps a little bit. So what we're going to do is look specifically at radon 222. So now in this graph, we told us that it has a half-life of 3.82 days. So for the ease of this argument, I'm just going to round up and say that a half-life is close to 4 days, okay, just to help this argument. So let's graph this out. So I'm going to have a y-axis and an x-axis. My x-axis is going to be in unit of time, and I'm going to be very specific. I want it to be in days. Whereas my y-axis is going to be my percent of sample. So we're going to start off saying we have 100% of our sample, right? So at 0 days, we have 100% of our sample. Now, we're going to say again, we say our half-life is 4 days. So 1, 2, 3, and 4. At 4 days, we have decreased our sample by half. So now instead of 100, we are at 50% of our sample. So I'll come over here and make a dot right there. All right, so now we're at 50% of our sample. 4 days later, we have another half-life. So 5, 6, 7, and 8. We come down here, and we are no longer at 50% of our sample. Now we are at 25% of our sample, so that's closer down here. Let's do one more iteration. So another half-life would be 9, 10, 11, and 12 more days. Half of 25 is closer to something like 12.5, so that comes down here. We have a really little dot, and so what you can do is kind of slowly connect the dots here, and you can see the path of the radioactivity decay, or the path of radioactive decay here. And so now my graph is not perfectly beautiful, so if I had done a good job of this, usually what it looks like is something like this. So you start off with a lot, 100% of your sample, you start off with a lot. Right away, after your first iteration, you're down to 50%. So you lose the most of your sample in that first half-life, okay? You cut everything by half. After that, it's just significantly less as you go on and on. So let's talk about one more example. I want you to actually solve a problem using this. And if you get stuck, draw out a graph like that. Sometimes it helps, okay? So here is the question. It's kind of long, so bear with me. Iodine 131 has a half-life of equal to 8.04 days, okay? What percentage of sample will remain after 32 days? Okay, what percentage of sample, assuming we're starting with 100%, will remain after 32 days? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's completely okay. So there's two ways of doing it. You could have done it like what I just did there, where you drew a graph and you completely map it out to get to the bottom, or you can do it in a table style. And since I've already done the graph, I'm going to show you a different approach to this. So one way is to say map out your day for one column, and then you want to just say your percent in your second column. So on day 0, the very first day, you are going to have 100% of your sample. Now, for the ease of this argument, we're going to say our half-life is about 8 days. So on day 8, we will have decreased our sample from 100% down to 50%. Our next half-life is going to be an additional 8 days, so 8 plus 8 gives me 16 days. From here, we decrease from half. So we're at 50. In order to decrease half, you go down to 25%. Same thing, another half-life. We go from 16 plus 8 gives me 24. So on day 24, we've decreased our percentage from 25 to 12.5. Now we have one more half-life that will occur at 8 to 24, and we're at day 32. Ding, 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 that's what we're looking for. So you divide 12.5 by 2, and we end up with 6.25% left over. Hopefully that made sense. If it doesn't, stop, ask your teacher, shoot me an email, and let's make sure we understand this. Have a great week. Take care of yourself. Drink water.